eliminate the parameter, and then sketch the graph of the curve given by x equals the square root of the quantity of t plus 1, y equals the square root of the quantity of t minus 1. First off, let's note that t has to be greater than or equal to 1 because y has a square root of t minus 1. And if t is never smaller than 1, then x is never smaller than the square root of 2. Just some observations that I made there. Now I'd like for you to pause the video and see what you can do about eliminating the parameter and sketching the graph here. Well, I've done some work, and just to be clear, the graph you're looking at is not correct, but let's see what we had by eliminating the parameter. Since x is equal to the square root of t plus 1, x squared must be t plus 1, and so t is x squared minus 1. Y is equal to the square root of t minus 1, and so y squared is equal to t minus 1. So t is equal to y squared plus 1, setting those two equal to each other, and then combining, whoa, that's not correct there. Gives me, well, setting those two equal to each other gives me x squared minus 1 is equal to y squared plus 1. Getting x and y on the same side gives me x squared minus y squared equals 2 with the constants together on the other side. Dividing by 2 gives me this equation, x squared over 2 minus y squared over 2 equals 1, which we may recognize is the equation of a hyperbola. And you may recall to graph a hyperbola, what we do is we take the number below x squared and square root it. That tells me how far left and right to go from the center. The number under y squared, square root it, and that tells me how far up and down to go from the center. We use that to draw our fundamental rectangle and then intersect asymptotes at the center through the diagonals of that fundamental rectangle. And then we draw the branches of the hyperbola to touch the fundamental rectangle and be asymptotic with those asymptotes. That's why they're asymptotes. But while the picture is accurate for this equation here, remember we had already decided that x was going to be greater than or equal to 2, and further, square root of 2, excuse me. And furthermore, y can't be negative because it's inside of a square root. So x will not be less than the square root of 2, y will not be less than 0, and so we're going to remove a few of the branches of this hyperbola, and our curve is simply the upper right branch of the hyperbola. Next up, same instructions, it'll be a slightly different pattern though. Here we have x equals the tangent squared of theta, y equals the secant of theta, and theta is restricted to go from negative pi over 2 to pi over 2. For this, it would be useful to recall that the tangent squared of theta plus 1 is equal to the secant squared of theta. Up till now, what we did was we've just solved for the parameter, and then we were able to do things algebraically pretty straightforwardly. Here, though, we're using a Pythagorean identity here. Since x is equal to the tangent squared of theta, in this equation here, I can replace tangent squared of theta by x. And since y is equal to the secant of theta, I can replace secant squared of theta by y squared. And we end up with the equation of a parabola that opens to the right and then has been shifted to the left by 1. Our equation ultimately is x equals y squared minus 1. Now we know it opens to the right because we have x equals y squared, positive coefficient there. As far as shifting 1 unit to the left, that's from the minus 1 here. And if I think about the equation y equals x squared minus 1, then I would know this opens up in the positive y direction, and it is shifted down 1 unit in the negative y direction. So that's what I'm using here. Shifted to the, opens in the positive x direction, shifted in the negative x direction. And that, by the way, answers the eliminate the parameter part. Now for the graph. If this is a parabola that opens to the right and is 1 unit shifted to the left on the x-axis there, then that should be my parabola, right? However, we have this restriction that theta goes from negative pi over 2 to pi over 2. And what I'd like to do is go ahead and picture the graphs of the tangent function and the secant function. And so that's what I've done here. We have y equals the tangent of x as x goes from negative pi over 2 to pi over 2. Remember, there are those vertical asymptotes. And then y equals the secant of x as x goes from negative pi over 2 to pi over 2. Doesn't look like a negative there, so now it does. And we have the kind of, I call them the cups, but this curve that points up. And the point I want to make here is that y is the secant of theta. Y equals the secant of x between negative pi over 2 and pi over 2 is never negative. So we know that y will never be negative in our curve. Furthermore, we don't actually have y equals the tangent of x. We have y equals the tangent squared of x. And that's going to have the effect of making it so that x is also never negative. Let's see if I can draw a facsimile of the tangent squared curve. It's going to be a little flatter here, and it's going to go actually up in along negative pi over 2 and pi over 2. It's going to go towards infinity both ways. So that's going to be y equals the tangent squared of x. And the point here is, as theta comes from negative pi over 2, it can't be negative pi over 2, but if it comes from that direction, x is given by the tangent squared of theta, and that y value is coming from like positive infinity. Same thing for y equals the secant of theta, or the secant of x. That y value is coming from positive infinity. And so as theta comes from the direction of negative pi over 2, we're coming from infinity and approaching 0, and then coming from infinity and approaching 1 for x and y respectively. In other words, our curve is coming toward the point 0, 1. And then when theta is 0, we bottom out on the tangent function, that value is 0. We bottom out on the secant function, that value is 1. And so we actually stop at the point 0, 1. And then as theta continues on toward pi over 2, the tangent squared of theta goes up to infinity, so does the secant of theta go to infinity. And so we have a curve that, let me adjust it here, is part of this parabola, and it comes from the direction of infinity, infinity to the point 0, 1, and then bounces back and goes back out to infinity. So these arrows go in both directions because the curve comes in and then goes out.